Okay, let's go ahead and get started. Um, just a reminder, if I looked at the calendar correctly, I think we have an exam next Friday. Somebody just gave me a thumbs up. So that'll be here. We are here today, and so we're talking about the Bode magnitude plot. I'm going to show you how I sketch it. This is not the technique that they use in the textbook, but I think it's a lot faster and a lot cleaner. Monday, there will be no new material. I'm just going to practice again this. So basically, the exam will cover the content up to today and Monday. The Bode phase will cover on Wednesday, but it will not be on the exam. Okay. Okay, not examined on it all. I'll save it for exam 3. All right. Any questions? Yes.
Is there any way that we could think about moving it to Monday? Because I know at least for the one, not that Monday, but next Monday, we have 3 tests next week.
I don't have a problem with it.
BMAC, because you could continue. I have BMAC too, and
The other thing I can do is I can do exam on 2 days. That's not a problem. We can take a quick vote here. How many people have conflict with this day? 2, 3.
3 tests that week.
What?
We just got 3 tests that week.
Oh, 3 tests in 1 week? Oh, that's nothing. Okay, let's stay with the schedule as it is published, and then you can go twist Dr. Wentworth's arm or whoever's teaching EMAG 2.
That would be against you.
All right. All right. So Bode magnitude plots. Okay. And so the technique that I'm going to show you is different than the one in the textbook. Let me first kind of quickly summarize the textbook approach. Textbook approach says basically the first thing what we do is we determine all the different components. Okay, so we plot each basic factor. Okay, and by each basic factor, that means we have the basic factors are just a pure gain. We have first order terms. And then we have second order terms. Okay, this is fairly easy to do these things. And then the next thing what they do is they say we graphically add them. Okay, we basically try to add the pictures together. This is a mess. Okay, this is a mess, and so I don't recommend doing it this way. It's easy to say, and that's why all the textbooks do it. They just graph all the different pieces and then add them up. And but I don't know of any practicing engineer who uses this technique. And so the technique I'm going to show you is the one that I've used over the years. Again, it's much quicker and gives much more satisfying results in my opinion. It's less messy. We will identify some of the basic terms, and then I'll go through a different approach. The technique that I'm going to use is on Canvas, since it's not in the textbook. Okay, there's an explanation of it, of notes on Canvas, and also an example. But I'm going to go through an example today. All right, so let's do an example. We are going to plot the frequency response of this model. There we go. Okay, so what we see here is a number of terms, basically what we desire today is we desire the magnitude plot of g of omega. G of omega means the frequency response. We're letting S equal to j omega. So let's first of all identify the basic terms. Number one, identify the basic factors. Okay. The first factor that I'm going to identify is what is known as the Bode gain. It's called the Bode gain. It is the gain on the Bode plot. It's very, very similar to the DC gain, but it's not the same thing. Okay, so let me put it on here. It's similar, but not always equal to the DC gain. Okay. So let me first explain the two. I'll write down here the DC gain. The DC gain is basically you let S equal to 0 everywhere. Okay. DC means no frequency. No frequency means S is equal to 0. Okay, that means DC. So if we let S go to 0, right here, I get a 5. I let S go to 0 here, I get a 10. I let S go to 0 here, I get a 0. I get a 360. So the gains would be 10 and 5 and 10 and 360. I would just add and divide those remaining numbers. Now for this particular function, if I let S go to 0 here, I'm going to get a divide by 0. So what does a divide by 0 yield us? What will be the number that results if S goes to 0? Infinite. Okay? So the DC gain for this problem is infinity. Some systems have infinite DC gain. A capacitor has infinite DC gain in the sense that if I put in a constant current to the capacitor, the voltage gets bigger and bigger and bigger and bigger. It will grow without bound, of course, until I reach physical limits. That's what it means. It just goes without bound. Okay? I cannot plot infinity on a piece of paper. So the DC gain is not very useful to us. In contrast, let's take the Bode gain. Now the Bode gain, again, I let S go to 0. But ignore terms that look like S or 1 over S. Okay? So if I let S go to 0 now, but I ignore this factor, now everything else is a finite number. And so the Bode gain in this case is going to be, in this case, it's going to be 10 times 5 divided by 10 divided by 360. So somebody pull out a calculator and calculate that for me. It's 5 over 360. It's 72. 1 over 72?
Yep.
Okay. And somebody convert that to dB. Take the log of 1 over 72 and then multiply by 20. Okay? Okay, so you see the difference between the Bode gain and the DC gain? If I had a factor in the numerator that was a S, and this S was not here, but it was in the numerator, the DC gain would be 0. And you say, well, 0 is a finite number. But when you take the log of 0, you get minus infinity. And when you convert it to dB, again, you cannot plot that. So the Bode gain ignores these two problematic factors, but it let S go to 0 everywhere else. Okay, do I have a calculation for 1 over 72 in dB? Negative 37 dB? Okay. So this is one factor we need to do. Identify the basic factors. First of all, let's identify the Bode gain. Okay, the next thing what we do is that we make a list of all the remaining factors. Okay, let's continue on. We've got the Bode gain. All right. Similar, but not always equal to the DC gain. For some systems, the Bode gain and the DC gain are the same, but not in this case. The next thing we need to do is let's identify other factors. I've got a 0 at omega equal to 5. I've got a pole at omega equal to 10. Okay, so this is the 0 at omega equal to 5 in the numerator. This is s plus 5 numerator. This is the s plus 10 denominator factor. And then here I've got a complex term. These are complex poles at, and what I got to do is I got to take this omega n equal to square root of 360. That's 6. No, it's not 60. Square root of 360 is, somebody is going to have to calculate that for me. $19? Is it exactly 19? 18.97. Okay, it's 19. Approximately 19. Okay, so these are the factors we need. Okay. Oh yes, there's this term here. Pole at omega equal to 0. All right. So let me write down all these terms again in a list. And what we're going to do is we're going to, I have Bode gain. I'm going to add that up at the top of my list here. And that Bode gain was negative 37 dB. Okay. The next thing what we do is let's label our axes. Now that we know the frequency range, we need to go, 0 won't be on our Bode plot paper. I just hand out Bode plot paper. So first thing you need to do, orient your Bode plot paper the right way. Okay, your semi-log paper the right way. Omega equal to 0 will never be on the graph, on the scale, on the horizontal scale, so we don't need to worry about that, but we'll plot its effect in a moment. And then we just got to make sure all these other frequencies can fit. So I'm going to suggest that maybe we put 1, omega equal to 1 right here. We'll put the exponent, we're applying the exponents, remember, at the major divisions. What it is in frequency is 10 to the 0, 10 to the 1, 10 to the 2, like so. So this is 1, 10, 100. And we'll label this as frequency, and the units radians per second. Okay. And what we're going to do is label this as magnitude in dB. Okay. This is the magnitude plot in dB. Let's put a scale on here. I think today I'm going to put 0 right about here. And call this minus 20, minus 40, minus 60, 20, 40, like so. Okay. All right. So what we've done is we've identified the basic factors, kind of summarize them right here. The next thing what we do is we label the axes appropriately. Okay. The next thing what I do is put breadcrumbs on the plot, on the frequency axis. Okay. Who here knows the story of Hansel and Gretel? Some of you? The rest of you were not well educated, did not have a good literature education when you were young. Your mother didn't read you Hansel and Gretel. Okay, what were breadcrumbs used for in Hansel and Gretel? To find your way home, right? To keep you away from getting lost. So that's what we're going to do here, is we're going to put some breadcrumbs. Now, what are our breadcrumbs? Our breadcrumbs are a reminder that we got to take care of some factors here. And we don't want to miss any factors. So the breadcrumbs I need to put on the plot are 5, 10, and 19. So I need to read this scale and put 5, 10, and 19. So I'll make a little breadcrumb mark. Here's 1. Let's zoom in a little bit and put our breadcrumbs on. 1, 2, 3, 4, 5. There's a breadcrumb. Something's going to happen here on my plot. Another one is 10. Another one is 19. This is not a very good example because I got all my frequencies so close together. I should have chose some frequencies that are spread far apart. This is 5, 10, and 19. 19 is pretty close to 20. Okay, so I put my breadcrumbs on the plot. In this case, it's on the frequency axis, and so the numbers are 5, 10, and 19. They have to go on the plot. Okay. Now the fourth thing that we do is we start on the low frequency side. Start on the low frequency side. So that means I pull out my frequency axis. I start on the low frequency side. That means over here. I start over here. And I plot, I get the initial slope correct. Okay? Start on the low frequency side. And the first thing we do is determine the correct slope. Okay? Now the slope is always going to be a multiple of 20 dB. Okay? It's a multiple of 0 plus and minus 20 dB. Okay? A multiple. That means the slope, the initial slope could be flat like this. It could be a flat line like this. Or it could be a line looks like this that rises at 20 dB per decade. Or it could be like this, which rises at 40 dB per decade. Or it could be a negative slope like this. But the slopes will always be a multiple of 20 dB. Or it could be flat. Okay? So we're going to determine the correct slope. Now, the way I determine the correct slope is I look at the factors that I have, and I say, well, this is a 0 at omega equal to 5. I know its initial slope is flat, and this is flat, and this was all flat. We saw all this on today's Friday. So we saw this on Wednesday when we were working on the computer. And we plotted these basic factors. They all start out flat until they hit a corner, and then the slope changed. So they all start flat. The one term that we did not do on Wednesday was this term, a pole at omega equal to 0. Well, we know that it's going to be initially flat, and then at the corner, omega equal to 0, it's going to change. But omega equal to 0 is not on the plot, and so what we're saying is by the time it gets to the plot, the slope is already negative 20 dB, like this. So for this example, in this case, we're going to start on the low frequency side, determine the correct slope. Here, we have one pole at omega equal to 0. So initial slope is negative 20 dB per decade. Okay. All the other factors start off flat, and then when they reach a corner, they change their slope. But this particular factor, it starts off flat, but as soon as you hit omega equal to 0, it changes slope, and it changes to negative 20 dB per decade. So what I'm saying is we need to draw a line on our plot, on our figure, with a slope of negative 20 dB per decade. So negative 20 dB per decade, let me get a straight edge. This might be a straight edge. Will look something like this. Okay? In 1 decade, which is from here to here, in 1 decade, I need to go down 20 dB. So it's this line. Okay, that's what I need to plot. I need to plot a line of that slope. But we all know the equation of a line. It's got two parameters. It's got a slope, but it's also got a y-intercept. I got to figure out where this line goes, up or down, like this. Okay, so I got to draw the line in the correct place. Okay. So I've determined the correct slope. Start on the low frequency to determine the correct slope. But the next thing I need to do is, because I'm at low frequency, I need to also determine other low frequency factors. The other low frequency factor is the Bodie gain. Okay, remember I let S go to 0 to determine the Bodie gain. I let S go to 0, but I ignored that term. I ignored this factor. Okay, so I need to take into account minus 37 dB. Okay, so this is what we do. We've determined the slope, and then the next thing what we do is sketch initial slope. In this case, it's minus 20 dB per decade. Sketch the initial slope passing through omega equal to 1 and magnitude minus 37 dB. This is a XY pair. Okay? This is an XY pair. So what I'm saying is I need to go find omega equal to 1. Here's omega equal to 1. And I need to find negative 37 dB, which is right about here. And I'm going to draw a line that goes through with this slope. Okay? So I find omega equal to 1 and the Bodie gain. Okay? If the Bodie gain had been 0 dB, then the key number is omega equal to 1 and 0 dB. So a lot of times what I do is I just mentally just go find omega equal to 1 and 0 dB. I put my pen right there, and then I just come down 30 by the Bodie gain. So this is the Bodie gain. I can determine the Bodie gain by going to omega equal to 0, 0 dB, and then measure the difference between where the curve is and that point right there. So that's the Bodie gain. In this case, it's minus 37 dB.
Why are you saying that frequency equal to 1 is omega equal to 0?
Did I say omega equal to 0?
Yeah.
I meant exponent equal to 0.
So to find the Bodie gain, do you plug in 0 or 1?
Okay, so to find the Bodie gain, I need to go to the point omega equal to 1, 10 to the 0.
Okay, so you plug in 1.
Yes.
Formula.
Yeah, I plug in 1. That's 1. Yeah. I plug in omega equal to 1, 10 to the 0. This is omega equal to 1, 10 to the 0. Yes, I go to this point, omega equal to 1, on the horizontal axis. On the vertical axis, I go to negative 37 dB. Okay? If the Bodie gain had been 0 dB, I would go omega equal to 1, 0 dB, and I would put it right there at that dot. But today, the Bodie gain is negative 37 dB, so I need to go to that point. And I need to draw a line with this slope going through it. Okay, so let me try to sketch that. Let's see, 1 decade away, I would be down to 57 dB, so that would be about here. 1 decade this way, I'm going to be 17 dB, that's about here. And so what I do is I draw my initial slope like this. Okay, give you a chance to absorb that. What I've done is I say sketch the initial slope. I first determine the initial slope by looking at all the factors I've got, and I see that in this case I have a 1 over S factor. I have a pole at omega equal to 0. So the initial slope has to be this, but it has to pass through this point, omega equal to 1, magnitude 37 dB, negative 37 dB. And that's what that is. A slope of negative 20 dB per decade. and it goes through this point. Okay.
So
Yes?
you would find that by putting in j omega for s and then putting omega into that, right?
I would look for what?
You put j omega in the original form. You put j omega in for s, and then you put 1 into the omega, and then you find the magnitude of that, right?
Are you talking about the whole function or just the one factor?
The whole function. To find the,
If you were a computer, that's what you would do.
well, I just did it, and it's not 37. It's like negative 36.
Because you put it in the whole function, right? The entire function. But I'm only doing one factor at a time. So if you did the Bodie gain and the 1 over s term alone, you would get negative 37 dB. Are you saying you put it into the entire function?
Yeah, because when you originally found the Bodie gain, you plugged in 0 for s, didn't you?
Yes. When I found the Bodie gain, let's go back to the Bodie gain.
What you're plotting it is 1.
Right. I think the confusion is why am I plotting it at omega equal to 1?
Yeah, if you're putting in 0, why are you plugging in 1?
Yeah. So to find the Bodie gain, I let s go to 0 everywhere. Okay. When s goes to 0, then all these gains come together. But I've ignored this term. What I'm doing right now is I'm doing both terms together. I'm doing this term, which introduces slope, and the Bodie gain, which introduces a gain. So this term, if you look at its gain, just look at 1 over s. What is its gain? Well, its gain is infinite. The 1 over s factor by itself, it has infinite gain. Okay, it goes up like this forever. If you go to omega to 0, it's going to go up forever. But the Bodie gain shifts the whole plot up and down.
Yeah.
All right.
But if you evaluate the whole function at omega equal to 1, wouldn't that be the intercept at 1, not?
No.
Okay, I'll ask you something.
Yeah.
That's what I did,
Yeah.
and that's not 37.
Right. You're saying that if I plug in omega equal to 1 here, 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 and here,
Yeah.
do I get 37? But you won't.
I'll ask you.
Yeah. Okay. You'll see a little bit, maybe why it's 36 when we get to these corners here. Okay, so, but that's a good question. It's not. I'm not saying you're wrong. You're correct, but there's a reason for it, and we won't know until you see the reason until you get further down. Okay, so we sketched the initial slope. 1, 2, 3, 4. We start on the low frequency side. We sketched all these initial slopes. Okay, number 5. We extend the line to the right. Okay, so we go in this direction. That's higher frequency. Okay, extend the line to the right, higher frequency. And we adjust the slope at each corner. Okay, adjust means this word. Change. Okay, so let's take a look at my breadcrumbs. I've got this term done already because I plotted the initial curve. I got this term done already because I adjusted the curve up and down. I got 3 more terms I have to deal with. I look at my breadcrumbs. I've got 3 more corners I have to deal with. So let me write again these 3 terms. I have omega equal to 5, omega equal to 10, omega equal to 19. This was a 0, so the change is plus 20 dB per decade. This is a pole, so the change is minus 20 dB per decade. And this is a complex pole, so the change is minus 40 dB per decade. one of our recent presidents got elected simply by saying we need change. So the key word today is change. When you get to a corner, you have to change the slope. Okay? So this is what I'm saying. Extend the line to the right. I got the initial slope correct. I got its height correct. I'm extending it rightward. I just continue going on until I hit a corner. So here's my corner right here. So what I do is I go, it'd be nice to have a straight edge, go to 5. Let's see, 1, 2, 3, 2, 3, 4, 5. So right about here, I need to make a change. Here's omega equal to 5. I need to make a change right here. Okay. So let's take a look at my breadcrumbs, my list, and I say omega equal to 5. It's a 0. The change is plus 20 dB per decade. So if the slope initially was minus 20 dB per decade, but the change is plus 20 dB per decade, what will the new line look like? It'll be flat. Okay? So what I do is I do this. I go like this. And I extend it to the right. Okay, so during here, this is flat now. I just extend it to the right. Extend the line to the right. Adjust the slope at each corner. So I've got this corner taken care of now. Now I got to take care of this one. Okay, that's at omega equal to 10. So that means here at this corner, I got another change to make. The change is negative 20 dB per decade, so therefore the slope should go back down like this. And now I've got the last corner to deal with. It's at omega equal to 19 or 20. And so here's another change. And it's supposed to be down at minus 40 dB per decade, which looks something like this. So this slope here is minus 40. What did you say? Yeah, you're right. 20 and 40 is 60. Okay. 20 and 40 is 60. So the change should be, if this is 20 and I add another 40, so it's 60. 60 should look more like this. Okay. So that's the straight line asymptotic curves. Asymptotic means that the lines are pretty good when you're far away from the corners. Okay? Now, if you put this in MATLAB, you're not going to get this curve. You're going to get a curve that's going to look something like this. It's pretty good far away from the corners, but near the corners there's going to be error. There's going to be a little bit of error here, a little bit here. The damping is a little bit low on this second order term. If you calculate, let's go back to our original model. This is a complex term, s squared plus 2 zeta omega n s plus omega n squared. So omega n squared right now is 360. You can calculate zeta. Zeta is kind of small. Okay, so that means the actual curve is going to have a peak right here. So it's going to go something like a little bit like this, and then it's going to do something like this. So the actual curve will probably look something like this. It should fall on this 60 dB, minus 60 dB per decade line. Okay. Now back to your original question. I plugged in omega equal to 1, and I did not get 37 dB. Because this, omega equal to 1 is within a couple octaves of this. And so there will be a little bit of error in the straight line approximation. If you threw away all those other terms and had something, some other term, say 1 over 72s, suppose we had g of s is equal to 1 over 72s. This has the same Bodie gain, but it's a simpler function. Then it'll be spot on. But those other terms are adding something here and something like that. Okay. All right. So that's sketching the Bodie diagram more quickly. Let me review what the textbook does. Okay. The textbook would do something like this. It would say, let's label our axes, 10 to the 0, 10 to the 1 right here, 10 to the 2. We'll label this as frequency. Let's put in our factors here, our gain. This is magnitude in dB. I'm going to call this 0, 20, 40, minus 20, minus 40. The textbook says plot each of the different factors. Well, let's take a look at our list of factors. Bring that back here. I have a factor at minus 37 dB, so I would draw a line at minus 37 dB. This is the Bodie gain. I have a pole at omega equal to 0. Well, 0 is not on the axis. 0 is not on the axis. What that means is the initial slope is going to be minus 20 dB per decade. So I would draw a line passing through omega equal to 1. That's omega equal to 1 right here, 0 dB. I would draw a slope that looks like this. This is the 1 over s term. Okay. I have another term which looks like a 0 at omega equal to 5. A 0 at omega equal to 5. So I got the Bodie gain. I got omega equal to 0. I got omega equal to 5 to do next. So omega equal to 5 looks like this. I would start off flat until I hit omega equal to 5, which is right 1, 2, 3, 4, 5. There's a corner. So then I would draw this like this. This is the s plus 5 factor. It does this and it does that. I have another factor, a pole at omega equal to 10. So it would look like this. Comes in flat until it reaches omega equal to 10, and then it drops at 20 dB per decade. This is the 1 over s plus 10 factor. Okay. All I'm doing is just drawing each factor all by itself. This is very easy. This is why the textbooks all teach it this way. They say find all your different factors, plot the gain, plot each of the different terms, what they look like. We have one more term, the complex term. The complex term is at omega n equal to 19. So it comes in flat until it reaches omega equal to 19, which is right about here. And then it changes, and its slope is going to be 40 dB per decade, which is something like minus 40 dB. So it's going to look something like this. A little bit more steep. So this is the 1 over s squared plus 10s plus 360 term. Okay? Fairly easy to understand. You just draw all the different factors. And now the books say, just add them together. So this is how you add them together. You say, let's see, I start off here at this point, and I say, what do I got? I got negative 37, 0, 0, 0, 0, 0, and 20. So that adds up to negative 17. So I would make a little mark right here. That's my first data point. And then I come over a little bit more, and I pick some numbers. Negative 37, and 0, and 0, and 0, and that's about 10, so it's about negative 27. So right here, I will plot at a point negative 27. So I will plot that in. Negative 27 is roughly there. Okay? And then I come over here a little bit more, and let's see what I got, negative 37, and 0, and 0, and 0, and 0, so it's all negative 37, so it goes through right here. I'm just adding every single curve together, bit by bit. Okay, so I come over here, I get negative 37, negative, I don't know, negative 10, and 0, and 0, and 0. So it's negative 47. So I'm down right about something like this. And I continue on. And if I don't make any addition mistakes, I should get this curve. Easy to do in theory, but it's going to be a mess because I got all these things to deal with. It's going to be a mess. So in practice, we use the Bode command on MATLAB or some tool to do it. Somebody's whipped out a nice pink calculator to do it. And but I do it this way. I just set down my breadcrumbs, get the initial slope correct, get its height correct, and just start drawing a line to the right. Each time I hit a corner, I change. All right? Your TI-89 has a frequency response plotter. I encourage you to look at it so that at least on the exam you can kind of look at your tiny little 2-inch screen and say, yeah, that looks like what I drew on the paper. So that's another tool you can do. Okay? If you learn to do that, use your TI-89 to do that, I think that's great. You're learning things beyond what I teach in class. I think you should get credit for that. So if you whip that out on your exam and do it, that's fine. I don't know about other calculators. What is that? That we'll do a frequency response plot?
No.
Okay.
So if we bring a printer, like
Yeah.
connects to our calculator, print out our graph.
Yeah, no printers allowed on it. Okay. Okay, so on Monday, I'm going to do another example. I'll try to get some numbers where the curves are, where the breadcrumbs are spread out a little bit more, and we'll do that. So we're just focusing on the magnitude right now. Next week, we'll also look at phase, but phase won't be on the exam. Okay? Yes, question?
On the negative 60,
Right here?
because you're already going negative 20 dB and then minus 40.
Yeah.
Negative 60.
Yes, it was going, between here and here, it was going minus 40. So beyond here, it should go negative 60. That might be a little bit more clear when